Right, guys. I think yesterday, the tutorial which I gave you, I said it was a preparation for this new chapter called complex numbers. I'm briefly going to start there by sort of showing you some kind of motivation why we need these kind of numbers. Right. Let's say with a question like solve the following quadratic equation. Let's just write the solve. The equation is 2x plus 2x plus 4 all squared. Maybe let me remove 4. 4 is not a nice number for me there. Let me write that. Let's just say 2x plus 5 equals, sorry. I don't know why I'm so confused. Plus 20 equals 0. Right. Now we'll solve that equation. Our attempt to solve that equation will be, first we can rewrite this as 2x plus 5 squared, and adding on both sides minus 20, we'll get 0 here, then that's equal to minus 20. I got here by adding on both sides minus 20. I didn't move anything altogether. I didn't change the sign of anything. Okay. So then after that, I think we'll be expected, I'm doing the normal way we do. We'd expected to find the square root on both sides, isn't it? So we can say now, applying the square root on both sides, obviously if you've got the square root, you calculate the square root of a squared, you must expect to get a, isn't it? So if I find the square root of this, I'll get 2x plus 5 equals to the square root of minus 20. What we saw yesterday in our tutorial is that this we cannot put in a calculator altogether. So now, but when we start solving this equation, our hope is to get a number here. But immediately this thing is not an entity which we know, then we say that is not real, isn't it? So continuing there, then adding minus 5 on both sides, what you get here? We get 2x equals to minus 5 plus square root of minus 20. That's what we done. Then after that, we'll divide both sides by 2. Dividing both sides by 2, I think you see that we get x equals to minus 5 plus square root of minus 20, all divided by 2. What is interesting for me here, why I'm doing this thing, is because actually this expression or what here, which we don't know what it is actually a mixture of what we know and what we don't know. What do I mean by that? That is, this thing is a mixture of what we know and what we don't know. Here, if we distribute this denominator as a common denominator, we're going to have 5 over 2, which is this a rational number, it's a real number, isn't it? Plus square root of what? Square root of 20, of minus 20, minus 20 over 2. I can even take this further and try to incorporate this 2 into the square root. I have to square it, isn't it? So when I find the square root of it, I get 2 again. So what is going to happen here? I'm going to have minus 5 over 2 plus square root of minus 20 over 4. Just check that that is reversible to that. Is that true? This is reversible to this, isn't it? I'll calculate the square root of 4, I get 2. Then I remain in numerator with the square root of minus 2, or minus 20. So then this simplifies to what? Minus 5 over 2 plus, let's don't worry about plus or minus because anyway that entity you don't know what it is. Then we divide here, we get the square root of minus 5. So this thing is actually a mix of what you know and what you don't know. This is a real number, it's a rational number. And this is, we can call this non-real. But at the beginning when we started solving this thing, we were hoping to get a number, isn't it? So that is where the problem is. Now this is a real number. Now, in our discussion yesterday, we did something that is, what I wanted to make you aware of is the fact that this type of equation have no solution because we can add this real number to this entity we don't know. We cannot guarantee that we can get a real number altogether. So then that was the question you asked yesterday. Then this is actually telling us that we are short of numbers because having equations like this don't have a solution. Maybe then that motivates that we should try to see whether we can maybe construct or invent another set of numbers which is going to give us solutions to that. Altogether. Okay. Now, important also which I wanted you to do in preparation for these numbers we're talking about, we looked at things like this. Let's say with something like this, 1 over 3 plus the square root of 5. The exercise here was saying rationalize the denominator. Then somebody will ask, what is this to do with the complex, with the nice chapter complex numbers we are dealing with? But for me, it is important that you notice that when we rationalize the denominator here, we called upon a 1, which was written in terms of the conjugate. We called it conjugate of this expression. And that expression was 3 minus the square root of 5. Then we wrote this thing as equals to 1 over 3 plus the square root of 5 multiplied by that 1 written in terms of the conjugate The reason why I want to make you aware of this and this term conjugate is because we're actually going to borrow this term conjugate and use it in complex numbers and see how it's going to help us. Is that right? But what's important now, you must now remember that when we multiply this thing, here at the bottom, at the denominator, we show that these were factors of what? Of the factors of the difference of two squares, isn't it? Then you must now see that we are going to have square root of 5 there. Let's say 3 minus square root of 5. Then taking the difference of two squares, we would get this as 2 squared minus square root of 5 all squared. It's very important to write this thing this way. You will notice that it's going to be very helpful to write this way because it will help you monitor your signs and all those things when you get to where I'm going to use this thing. Then this ends up with what? 9 minus 5, isn't it? So we get here and say 3 minus square root of 5 over 9 minus 5, that's 4, isn't it? 4. What is important again for me here is that notice that this you can also separate into two things. One which is rational and the other which is not rational. But at least this is all real, isn't it? So then we could separate this thing as 3 over 4 minus square root of 5 over 4. Now what have we done here? We've come up with a number which is actually kind of a composite number. What is it made of? It's made of a rational part and the irrational part. All together. You understand? So what I'm trying to invite you to here, I'm trying to invite you to the idea of writing a number as a composite of two different things, which are basically two different entities. Now in this case here, this is irrational and this is rational. And the product here, the sum or the difference is a composite of the two. And fortunately, this is a real number. But in this case here, this sum here is not a real number. All together? Okay. Now, I'm going to invite you to do this one now. Someone's going to come and work on the board, something like this. Let's look at something like this. All this, understand this, guys, as a preparation to work with the new numbers. We've already there, the name is suggested complex numbers. I repeat, I said this thing yesterday. This way of saying complex numbers shouldn't confuse you to mean complicated numbers. What does it mean? It means exactly this. These are numbers which are sort of composite. In other words, they are composed by being written as a sum or a difference of two different entities altogether. Okay, not squares, no. Don't take the chorus of difference of two squares to this. Okay, altogether. Now I want you to do this. I'm inviting you to handle this one. I've got 2 here over 3 plus square root of minus 6. I'm asking you to apply the same kind of manipulation, take into account all the uses, the things about conjugates. Actually, let me not use the plus sign here. I want to put a minus sign here. Taking all those ideas on conjugate, and I want to develop this to the form, maybe something here, packet which you know, plus maybe something this side which is, in this case, probably unknown. Obvious, why do I think there's something this side unknown? Because this already is unknown. But I want, all what I want, I just the technique of manipulating that thing to take it to 2 parts. Can you do that, please? I want somebody to come and do it on the board and give me the final answer there. All together, guys. Please push your pen against the paper and give me that. Actually, now we're just like working with some kind of nonsense, but we've got a way which we borrow from what we know to work with it all together. But then what we're going to do, we're going to see if we can mine some sense from this kind of nonsense. All together, guys. Do you understand what I'm talking about now? We're just using the manipulation skills to manipulate that nonsense, but at the end we try to see if we can mine some sense from that and then move forward and see what are these entities, mathematical entities we call complex numbers. Right, I'm giving you some minutes to work. Right, according to what you've got here, this has been simplified and been separated into 2 packets like this. But in this case, we get one result here which says this is equals to, let's maybe do it quickly together, is 2 over 3 minus 6, square root of minus 6. Now multiplying by the conjugate will be 3 plus square root of minus 6 over 3 plus square root of minus 6. Actually, now as I'm working it, I don't know how that guy got that thing there on the board. But anyway, let's correct it together. What will happen here? We've got the difference of 2 squares in the numerator. Just look at something here. There's something very interesting about this thing here. Look at this. This entity, 3 plus square root of minus 6, It's an entity which is unknown. And this one is also an entity which is unknown. But let's apply the square root of the factors, expand this as the difference of two squares. What do we have? What do we have? We've got 3 squared minus square root of minus 6 all squared. And then in the numerator we've got what? We've got 6 plus 2 square root of minus 6. Look at the denominator. The denominator is interesting. Just focus on the denominator and see how why I'm saying the denominator is interesting. This is 9 minus 6. And at the top they've got 6 plus 2 square root of minus 6. I can say, let me just use maybe vulgar language here and say, what we had here is a heap of nonsense. But we manipulate it as if it was a square root of different two squares. What do we get? We get a number, a real number, isn't it? I think that's a sign that maybe from this nonsense we're multiplying here, we're going to get something. Do you hear what I'm saying? Yes. From what I'm seeing the denominator there, this is a suggestion that maybe from this kind of nonsense, we're going to get something. Let's see. The denominator is already a rational number, a real number, but it basically comes from some kind of nonsense. Let's say, what do we have there? We've got plus 15. So this becomes 15, and there's 6 there, plus 2 square root of minus 6. Now, putting this thing in 2 packs like this is just to distribute this denominator. Then we've got here equals 6 over 15, which is actually 2 over 5. Then that's a rational number, real number, plus some piece of non-real over 15. And again, this is a kind of what? Composite entity. Why I'm repeating this thing composite entity? Because I'm saying complex number does not mean complicated numbers. It means composite numbers which are composed. They are composed of 2 parts. Altogether. So what I can say already here, somehow, the structure of this number called complex number is already been suggested. Altogether. So guys, all this plus what we did yesterday, I call it motivation for complex numbers. To see the need, why we should get complex numbers. In mathematics, just pure mathematics, my interest would be just to solve this equation. In electrical engineering, I asked you to go and find out yesterday. Indeed, I said try to go and find out, and I talked to you about this thing of active components and the passive components, or active and reactive components. Indeed, all together. Okay, I'm going to pause here for a while. Take a full scale paper, write what you found out in that task on a piece of paper. I repeat, guys, from here up to the end there. This is what I call motivation, and I think you are ready to welcome this new number we are going to call a complex number. Just one thing which I want to talk about. Just one. Let's just take this square root of minus 6. This will be important also. Just notice that square root of minus 6 is the same as the square root of minus 1 times 6. Is that true? Then this is actually square root of minus 1 times square root of 6. This also to me is beautiful. Just like this. This was nonsense, multiplying nonsense, and you're getting some real number there. And this is also beautiful. Look at this. Now we've got a product of a real number, a rational number, and this entity which is not known. All together. So if I can quickly maybe just before we say what is a complex number. If I had an equation like this, 2x squared plus 2 equals to 0, then this would give us 2x squared equals to minus 2. Dividing both sides by 2, we will get x squared equals to minus 1. And then this translates to, therefore, x equals to square root of minus 1. So our whole problem, which we are talking about here, we're actually talking about the square root of minus 1, nothing else. We had the square root of minus 5 there, minus 6 somewhere there, but all that reduces to talking about the square root of minus 1. That's a simple, that big equation which I gave there at the beginning, there. Also, this 20 is just the same as square root of minus 1 multiplied by 20, which reduces to square root of minus 1 times square root of 20. So you see where our problem is hinging, isn't it? So now, what is a complex number? Let's come to the idea of complex numbers. That's it. So first of all, I'll remind you of what we said yesterday. I remember, before we go to real numbers, which are represented on the real line, we had rational numbers. And we showed you that if we've got a rectangle, a right angle triangle like this one, where the hypotenuse is 2, this length is not represented by these numbers. You remember that? Then what happens now? Then what we did is, if we put this length from 0 somewhere there, we will see that we will get that square root of 2 lying somewhere here. Then that means that this kind of triangle, which you can put here, and then rotate this way, and put it this way, with the hypotenuse from 0 to there, you will see that after 1, we've got, let me just adjust this. After 1, we've got something there which can call square root of 1. Indeed. So we then show that this was presenting us with not enough numbers because we didn't have something to represent the hypotenuse of that triangle. All together, guys? So now, again now, with real numbers, we were just seeing that we don't have a solution to this type of equation. X squared plus 1 equal to 0. And this is a beautiful equation. The equation which I used it to is what? It's a quadratic equation. And most of the quadratic equation we had the solution, but this one doesn't. And actually, the solution to this one, if it had, it would have a solution to the one we started with. We would have a solution to the one we started with. All together. So now, what is the story? Now we're coming to the idea of complex numbers. Let me just, I want to remove this clear, okay? Let's get this back. Now, after, I don't know, after how many thoughts, after how many ideas, people are struggling to solve this equation. I think it's logical for somebody to think this way. If all the points on this number line represent numbers, and every number is a point which it represents, in other words, there's kind of a one-to-one correspondence there. Numbers to a point, point to a number, everything covered. Then I think it's logical for someone to say, isn't there maybe other points are outside the line which are also representing numbers? That kind of a thought leads to an idea that maybe there's another unit besides the unit the one as a unit. Another unit. That's interesting. Another unit outside the number line. So that kind of imagination, I emphasize on the power of imagination. The only thing I like normal human beings is the use of the power of imagination. Think of anything you've got, maybe a car, whatever, an aeroplane. If you think how that thing came about, it is because of the power of imagination. All together. So now, something, maybe there's a number outside there. Then okay, what do we have which offers us a system? Is a system of coordinates, xy coordinates. Now, if we now take this one as a real coordinate, as a real unit, 1, can't we maybe think of another unit along this line which we can call imaginary unit? That's the question. So now, let's call I imaginary unit. What is our wish? Our wish that if such a unit exists, then that unit squared must give us what we don't have. What is this? This equality gives us the square root of -1. Because now what we can say here, we can say this is equivalent to saying the square root of I squared is equal to the square root of -1, but here is I squared. Remember, square root is power half, and the 2 there. You then get this equals to I. So from today onwards, guys, welcome to the world where there is an imaginary unity and it's called the I, and you square that imaginary unity, you get -1. As they would say in French, voila, x squared plus 1 equals to 0. He has got a solution. What's the solution? X equals to the square root of I squared, which is the same as the square root of -1, calculating here, which we get as plus or minus I. Plus or minus I there, minus I here. 2I there, 3I there. I didn't write I there, made a mistake there. I didn't write I here. 2I minus 2I. Let's clean this a bit. Are we following, guys? Are you following? I'm talking to you. Say minus 3I. Now, listen to me. This becomes a real axis. And this becomes the imaginary axis. What do we have on the imaginary axis? Imaginary numbers. What do we have on the real axis? Real numbers. Interesting. Interesting. Look at this. On the real number line, we've got real numbers. On the imaginary number line, we've got real numbers. And all those things are points. What about points outside? Check this. Now here, I'm appealing to your knowledge of vectors. I'm appealing to your knowledge of vectors. Check this. What about numbers? The question is, what about numbers outside the points outside what? Outside this real axis and imaginary axis. Look at this. Well, let me put it this way. If we're in the chapter on vectors, what would you say? We would have I here, J there. But we don't have I here. These are real numbers. These are not vectors, this is a real number. And we've got I there for imaginary. So now, this head here is at a point. It's a head of a vector, and it's at a point. But now, this point here, we can give it a notation of a number, a special number which we have today. What are we taking from? We're taking from our previous presentation. Look at this. Here, we said there, we can take this this thing into a composite form where there's a rational here, irrational there. And then further, we took this to a composite form where we've got real there and non-real there. So now, coming to this case, can't we then take this thing as 1 from down here plus 2i and call this a composite number, but mathematically we say a complex number composed of the real part and the imaginary. Guys, from today onwards, you know what is a complex number. What's a complex number? It's a number with a structure x plus I, y. That's a complex number. Then the question comes, what can we do with these entities? What can we do with these entities? And these are mathematical entities. What do we wish? I mean, a normal person, if I was in a bakery, I would wish that everything was flour so that I can bake more bread. But this is mathematics, these are numbers. If then we wish that these things could be like the usual numbers be added. Like the usual numbers be multiplied. Like our usual real numbers that we can perform division. And if we can add, we can also perform subtraction. So now we've got at the end of the day now to answer this question. But there's one important thing we've answered. There's one important thing we've answered. These types of equations, now we've got solutions. What is the solution here? I've already separated here. This number now would come to minus 5 over 2 plus square root of minus 1, sorry for that, square root of minus 1, square root of 20. 20 is the square root of 20 is a real number, over 2. Then at the end of a good discussion, this is minus 5 over 2 plus I square root of 20 over 2. And that's the kind of entity we've just called a complex number. Guys, is it not beautiful? To me, it looks very beautiful. I'm sorry if you don't have the eyes to see the beauty, but this is beautiful. Now, if you really did your homework about the active part and the reactive part in that electrical situation I talked about, now you should be able to tell me that this is the active part. I'm not pointing at the right thing because I'm not an electrical engineer, but you should be telling me now which one is the reactive part, which one is the active part. All together. So I'm giving you further investigation. Go and investigate and find out which this is kind. This at the end of a good day, guys. This is a model. This is a model. Like I'm now saying, it involves talking about active part and the reactive part. You must be able now at the end of this course or at the end of this chapter to be able to say, here's a complex number, this is the active part, this is the passive part or reactive part and active part. Am I understood? I said go and do your homework. The day of judgment is coming. Okay. Right, guys. I'm happy I've got something I can call a complex number. I've got there something I can call a complex number. Now, let's move forward. Now, let's come to this stage. Operations with complex numbers. Let's say we've got Z1, which is 3 plus 4i. And Z2, which is 5 minus 2i. Maybe at this point, let's correct something here. Let me make a comment here to set you somehow comfortable. In electrical engineering, I is a reserved symbol. Tell me for what? This is a reserved symbol for current. Just read that symbol there, dot dot equals, meaning this means current, isn't it? So that causes some noise in the system. For mathematics, I don't have a problem with this. It's imaginary, it's imaginary. But if you don't want to get some confusion in electrical engineering, we normally write this thing as 3 plus 4j. We just borrow j and basically call it I for imaginary. Altogether, we'll call this thing imaginary number. 4j is imaginary number. Then this one, then we write as 5 minus 2j. So then if you go to a book and you find a j, don't really get surprised. And you go to another book, you find an I, just check whether the book is electrical engineering biased. Altogether. So, isn't it? So, gentleman's agreement, j squared equals to minus 1. That's a convention we're going to adopt for this course. Comfortable? Now, let's say z plus z1 plus z2. Listen to me. I would invite you at this stage, hold your two hands with your palms, your inner palms facing each other, like I'm doing. Put your hands together, your fingers match. All together. The idea of matching components is the one you're going to use to add your complex numbers. Am I making sense? Good. Let's go. Then what do you do here? Then you say here, 3 plus 4j is first day today. I'm going to do it slowly. Plus 5 minus 2j. Is that right? Then the next thing, I'm going to bring my corresponding parts together. What am I going to say? I'm going to say 3 plus 5 plus j brackets 4 plus minus minus 2 all together. Then I now do the number crunching. Just combine the numbers the way they are suggested there. Respect the combination of signs and all those things. All those rules of algebra are applied here. Why is j standing here? J was a common factor. I factorized all together. So all the other rules of numbers will apply now here. So then this is 8 plus 2j. All together, guys. Any questions there? Then let's do the subtraction, which is very, very similar. I will say now z2 minus z1. Then this is 5 minus 2j. Everybody now understand why I'm saying j, isn't it? Minus brackets 3 plus 4j. Again, the matching principle applies here. All together, guys. So then what do we do now? We bring matching components together. Then it's 5 minus 3 plus My plus is for that composite number. Altogether, it has nothing to do with the subtraction. Is that the complex number is a composite of real, one thing from the real, plus something from the imaginary. Then I take my numbers with their signs as they are given. The numbers are minus 2, minus 4, J. As you can see, this side I've written J that side, and this side I've written J the other way around. It doesn't matter. Isn't it? 2 times 3 is equal to 3 times 2. Then, this is what? 2. Then there we get plus minus 6J. That's what we got. Then you apply the combination of sign rule. Then you get 2 minus 6J. If there's anyone who doesn't understand what I'm doing, guys, I've stopped. I'm listening to somebody who wants to clarify something. I'm not trying to be funny. You take this thing to a very kind of hyperactive child in grade 7 or so. You show him this thing. He or she will do it with no problem. Why? Because this looks more mechanical than anything. I don't explain all those things I explained for you before. I just show him this thing, him or her, this thing, to play around with this thing. I think I'm going to get correct answers just for this edition. What do you think? What do you think, guys? Try it. You've got young sisters and brothers at home. Try it. Just show them this thing and try to play around with it. So there's no reason for forgetting this thing. That's what I'm trying to say. Can I say addition done? Can I say addition done? So, done. What is this about? It's about addition. Subtraction and addition, of course, done. Questions? If there are no questions, I'm moving fast forward. Right. So there are no questions, let's move. Let's just do this thing for a while now. Let's come to multiplication. Let's come to multiplication. Quickly to multiplication. Now, questions. Why do you think your grade 7 teacher taught you this? You never knew. You thought he was crazy. He was not crazy. He knew that we were going to do complex numbers at university. Because now, complex number, I've just added a J here. A J there. And I know that a J, whenever J squared, is going to give me this. Altogether. So now you can see also the tutorial which I had with you. Why that kind of a tutorial? You thought, this guy is crazy. He comes and asks us to multiply A plus B multiplied by C plus D in brackets. That is grade 7 work. Oh, it's grade 7 work. Okay, it's fine. Let's do grade 7 work. Let's do grade 7 work. Should we? Z1 times Z2 equals 3 plus 4J multiplied by 5 minus 2J. I'll do it the long way. Hello? Let's do it the long way. All right. Now, let me do it this way, like we would multiply 12 times 13. 4J. And what do we have here? 5 minus 2J. This is the way I would lay out the multiplication if I was multiplying 12 plus 13. These would be units. These would be my tens. I'm just trying to strike some similarity there. All together. Okay. But normally, if you multiply tens and tens, you get hundreds. Isn't it? So that will give us here You cannot multiply tens and get something falling under tens. No. So it will be out of there. This will be 3 times 5. All together. Now plus. If I multiply tens and the units, I'll get tens. Then I get here 5 times 4j. Are we done? Then I multiply here, there, I'm multiplying units and tens. I'll get tens. I get what? Minus 2j multiplied by 3. Units and units, I can get units. So then what I can get there, I'm going to get plus 4 plus 4j multiplied by minus 2j. And warning, it's very important to use your brackets and handle your signs very carefully. Otherwise something is going to go wrong. Let's multiply here. I get 8. What do I get here? I get minus 6j. And there I get 20j. So it's 20j minus 6j. What's the answer? 20j minus 6j. What's the answer? 14j plus 14j. Good. Then let's organize this thing a bit. Let's get this thing more organized. Can I have silence there, please? Then you get this thing plus 4 multiplied by minus 2 multiplied by j multiplied by j. I'm just bringing like things together. Okay, let me pause there for a while. Sorry guys, I think you see that this is a bit abnormal here, isn't it? All together. Multiplication was interpreted as addition, isn't it? So please, just, I think that was just a slip of a tongue of a pen. Let's correct that. That is 15. All together. Now what have we done here? We just brought like things closer to each other. J times j, which is j squared, minus 2 times 4, which is minus 8. So we're going to get here 15 plus 14j minus 8 multiplied by j squared. But j squared has got another meaning. What is it? Minus 1. So it's minus 1 times minus 1 is plus, isn't it? Then we get here 15 plus 8. Because once it gets plus, then it becomes real, then it comes closer to the reals. Then we come here 14j. Are we together, guys? Okay. Then our answer, we can now write our answer there. I just put it there so that because I wanted to multiply in detail. Are we together? But we could have continued here with the exercise multiplying in detail, whichever way you want to do it. If you don't want to do it this way, as if I'm multiplying 13 times 14 times 12. So now your answer now becomes 15 plus 8, 23 plus 14j. Are we together, guys? Good. This is how we multiply that. And I'm not going to repeat this example. The examples we did yesterday, multiplying all those things, they were all preparing to do this thing. The only thing you need to master here is that j squared is equals to minus 1. That's the only new thing which is coming there. Those numbers are labeled 14j. It's just telling you that this 14j lies on the imaginary axis. This 15 is not labeled, lies on the real axis. The sum lies as a point somewhere there. All together. Again, coming back to here. This thing as I drew it here was a vector. It looks like there's a very strong marriage between vectors and complex numbers. Because where there's a complex number, it's a head of a vector. So, in simple common man's language, I can say, there are as many vectors as there are complex numbers. Isn't that beautiful? It sounds beautiful. Once I get hold of a vector, I know, sure, I'll get hold of a complex number. What do they share? the magnitude. We're still going to talk about that. And as it is, I can even ask you to calculate the magnitude of a complex number. You'll get it easily because you know, you have seen what it is. The magnitude is still the magnitude of that same vector. The angle is still the angle of that same vector. But we're going to get engaged with that in more detail. Guys, up to this point, are you happy? Right. Let's come back to this slide here. Now, I want to show you something here. Now, I'll write things like this. We will write things like this. Something like this, you must be able to read it back to yourself. This says, extract the real part of the complex number Z. That's what it says. Then this one. This one says, extract the, what do you think? The imaginary part of Z. Now, let's check whether we understand what we're talking about here. Let's check whether we understand what we're doing. Then I write re 3 plus 4j. That's the complex number Z. I've already indicated there that the complex numbers, real numbers, we usually use X for real numbers. Complex numbers use Z because we compose that Z with the X component and the Y component. Are we together? Okay. What do you think is the real Z here? Come again? 3. Good. Normal people answer this one correctly, and they don't answer this one correctly. But it's good to make a mistake, then we are told it's a mistake, then you learn that it's a mistake. What do you think is the imaginary part of this one? Come again? Sorry? What is it? It's 4. You can't say 4j because j is labeling that this is from the imaginary axis. Or I says well, but the imaginary part, both of these two must be real. All together. As you can see, this is a real number, and this is a real number. End of a good day. A complex number is a composite of 2 numbers, but one of them is extracted from the imaginary number. All together, guys? Good. Questions, if there are questions. Let's come to the last thing now. I think this is going to be the last one. Division. Division, we talked about conjugates then when we were changing our, rationalizing our denominators. We talked about conjugates. Now, let's divide 1 by 5 minus 2j. But we want to write this thing as a complex number, as a composite. That plus j, something like that. It is still a complex number as it is, but we want to divide and write it this way. What are we going to do? We're going to use the idea of conjugate we talked about when we were rationalizing the denominator. Then suggest, what do you think we must do here? I'm asking you, what do you think we must do? Multiply by what? 1 in terms of the conjugate. I like that. 1 in terms of the conjugate. That sounds nice. That sounds. Where did you hear that, my friend? Where did you hear that? We talked about it the other day. Mzilikazi kama showa. Sure. Hayi, ngajabula inkosi yami yakhuluma into engcono. Mtungu. Right. So 1 in terms of the conjugate will be 5 plus 2j. All together. So remember that situation, in this complex number situation, in that rational denominator situation, the conjugate, they just differ by the sign in between the two composing parts. All together. So 5 plus 2j. Beautiful. Denominator, what do we have? Factors of difference of 2 squares. Then we write 5 plus 2j over 5 squared minus, what am I writing here? I'm writing the difference of 2 squares as I know it. A plus b multiplied by a plus minus b equals a squared minus b squared. So here I should write 2j all squared. Please, advise, don't try shortcuts before you have embraced the situation fully, before you have got experience. Are we together? Then we'll separate that. That will be 25. That will be minus 2. That will be plus 2, isn't it? That will be 27. Then we got that thing as 27 denominator. Are we together? 25 here, minus 2 here, minus 2. No, minus 4. Sorry, minus 4. Then minus 4, 29. Then you go 5 plus 2j. In a composite fraction, 5 over 29 plus 2 over 29j. Are we together, guys? Now, I invite you to go to your textbook and pick as many complex numbers as possible. I said as many complex numbers as possible. Do division, do multiplication until you feel you are like a sponge on a saucer full of water, having embraced all the water. Thank you for listening.